continuing on, mapping and trying to figure things out. Instead of telling stories, figuring things out, we've talked about angles, right? Around and up. So we've done angles. We've also mapped your sky with those angles, looking up or looking around with those angles, right? Up or around. We can use angles to map Earth, and we can use angles to talk about where things are relative to each other, the stars. So when we map your sky, which we did last time, we're talking, sometimes people say your local sky, your ground. But what you see is affected by where you are on Earth. So we're going to talk about that. Where you are, I mean, if I'm here, right, we're really teeny tiny, so our ground looks kind of flat, doesn't it? It looks kind of flat. And you look up and you see that, but you can't see anything below your ground. I can't see anything down there, even though there's a big Earth. If I'm down here, then she gets to see this, that. Where you are affects what you see, okay? And even what time of day as you spin around once a day. Of course, they didn't know that. And that brings up an interesting question, a couple of interesting questions. One is, well, let me bring that in, actually, to the next question. And the question is Earth flat? You know, you might come across someone that says Earth is flat. Not too many, but there is kind of this, I don't know, everybody's looking for something crazy or some conspiracy or something. It's just a lot simpler if there's good guys and bad guys, just like simple movies. Is Earth flat? Well, for a long time, you might be surprised, people have known, make sure you can see this, that Earth is not flat. And a little checklist here, maybe I should put it in the book, of 6 reasons you could tell your friend how we know Earth is not flat. Kind of simple things. One is, since antiquity, when something casts a shadow, you see its shape. Right? Look at my hand. You can see how many fingers do I have? I guess you count thumb, whatever. Right? How many fingers am I holding up? You can see it. But of course, that's got to hit something. So you know that big idea, anything around the sun, a big light bulb in space, the side facing sun is lit, the other side is dark. It's for Earth, that becomes, we spin into the light, day, out of light, night, and Earth casts a shadow. And as we said in chapter 1, eclipses happened and they kind of freaked people out, right? So, but they were noticing. And when an eclipse happened, again, you don't see the shadow, so that would make it easy. But what you do have, as the moon enters the shadow, and this is known a long time ago, the shadow hits moon's surface, and on that entering edge, you can see the curve of Earth, and on the exiting edge, you can see the curve of Earth. It was known for a long time. That was just one of the things that was known. Here's another thing that's well known, and that is, if you're traveling, and this applies to a lot of objects. If you're traveling and some object you only see in the distance, a tree or a pyramid or something in the distance, and you only see kind of half of it. You don't see this bottom part down here because it's below your horizon or something. So, but you don't know that necessarily. But you keep traveling, and of course it looks bigger. But not only that, you start seeing this part. Why do you start seeing this part? Because you're not traveling on a flat surface, you're traveling on a curved surface, and it starts being above. Here it's below my ground in the distance, if you will, my horizon, if you want to call it that. And now as I go down, it rises up, right? It rises up, and you can do that. Ships at sea see this, saw this. People traveling saw this. They even were able to, thousands of years ago, able to measure the curve of Earth, looking at shadows and just clever things. So just when you travel, you know, at a distance, things, even, it doesn't have to be that far, you can really start to see that you're traveling along a curve. That's number 2, lunar eclipse. Number 1, The other thing is, what about this? What about, do you believe that South Africa exists, Argentina exists, Australia, New Zealand, they exist? If you believe they exist and you go there, okay, then you go there and then maybe you'll believe it. And then you go, I wonder why it is that they don't see Polaris, the North Star. Why don't they see Polaris, the North Star? The North Pole, it's at your zenith. We're going to talk about this in the next video. But as you move, just like I said before, where it is changes. Why? Because you're not going like this. You're going like this. And then you can't see it. You can't see. There are stars that you can't see from down here. That's because Earth is round. I probably don't need to convince you, but sometimes we hear some people say it, and they say it with such conviction, and they've got all these arguments, and you go, wow, well, maybe. I don't know. I never thought about it. I'm sure I could be gullible to some things, but then you go, well, it's not accepted, so maybe I should check that out and challenge that. If of course, spacecraft, how do you orbit a flat Earth? What is that? The satellites that affect our phones, etc. How does that even work? And when you get in a plane, you can even see the curve of the horizon. So what happens? How do you travel around a flat Earth? So that doesn't really, and it's easy to see. You can just see. You get off and you see the curve, and you can, etc. And then gravity. How gravity works? Point number 5, I guess. Is, in fact, you couldn't orbit, we'll talk about that in chapter 2, without gravity and the way gravity works. And everything that we know about gravity that gave us an understanding of chapter 0 and lets us use GPS, we couldn't use it. There's some subtle stuff to make that work well, et cetera, et cetera. Everything that we know in our theories to make stuff and everything we know in detail about gravity says that things, chunks, solid chunks will come together and pull together and sift into basically a sphere. Okay, now this is spinning, so it's a little squashed, but basically a sphere, a ball. So everything we know about gravity also says that. In fact, kind of a cool thing about gravity is that down is not this way. Down is, well, it's towards here. So if you stand on the South Pole, your hair doesn't go like this. The only thing wrong with turning this upside down is that the words are upside down. So. But the reason we often do that is most people live in that northern hemisphere, which we're going to talk about right now. We're going to map out Earth. And the other thing is, so what, we're supposed to be on a flat Earth looking up at this thing? Moon? Sun? Kind of round, right? So I don't quite get it, but probably worth addressing. There you go. We're going to map Earth. And we're going to map Earth and relate that to what we can see. And I think we'll have some pretty profound little revelations. Okay, it won't be too bad. What's our objective? All right. Well, we want to be able to specify any particular place on the Earth globe or on Earth, a specific, not so much direction, but a location or address on Earth, and what is going to be given by, again, 2 angles. You know what they are, latitude and longitude. We'll talk about what those. A lot of people don't know that because we don't need it. It's fine, but it's not that hard. So you might as well learn it. And it is a concept that's important in astronomy, especially latitude. So we will map Earth and talk about that. Here's Earth. Here's an Earth. It's a magnetic Earth. Such a magnetic personality. And if I grab it, oh no, there's a magnet in there. We know that Earth spins, and so the 2 geographic locations around which it spins now, it doesn't feel like you're spinning. It does not feel like we're spinning. At the equator, the speed is about 1,000 miles an hour. San Francisco, Washington, D.C., we're going to look at that in a second, across the U.S., about speed of sound, about 700 miles an hour. So we're going fast, and there's a reason why you can't feel that, and that is at the end of chapter 3. So we're getting there. Of course, if you map out Earth, you've got North Pole, South Pole, equator. And I can draw it fancy, which would have me tilt it. Maybe you can see it better. Here, North Pole, and if I tilt it, this comes here, and then this goes back. It's kind of hard to draw. You'd be able to kind of see, if you imagine it see-through, you could see that goes back as a circle. So the nice thing about that is you see it as sort of appearing 3D, three-dimensional. Drawing it this way is just easier. So I'm going to certainly draw it this way. And of course, this is the north hemisphere, and this is the south hemisphere, as you know. So the equator divides Earth into the north and south halves, or hemisphere. And if you've seen South Park, I should be wearing my Canada t-shirt, but if you haven't, well, you'll just have to watch that someday. There we go. So let's get over and map Earth. Make some quick work. You got this in the book, right? So we're going to talk about this. Oh, I did that, didn't I? I was going to show you how I made those circles. I mean, of course, I just made them because how I did it, and this is relevant to chapter 3. A little bit of a preview. Remember how well that works? I took it, put it in the center. I tied a knot so it wasn't so long. Tried to make the right size. And then I just went like this. And I keep the same distance all the way around. And that's what we call a circle, equal distance from the center. In chapter 3, we're going to do that and make an ellipse. We'll talk about that. All right, so that's Earth and that's Earth too. I just want to mark them up differently. What do I need? I need North Pole and South Pole. Let's do this. I'm going to put NP. We don't need to write North, right? We can just use abbreviation. NP. You can put the dot or not the dot. I don't care. NP, that's going to be useful. On the South Pole, Antarctic. Watch those ice sheets, right? South Pole, South Pole. All right, cool. And so Earth spins around that line or axis of rotation. But again, cheating. No one knows that yet. We're getting our way up to that. And then what else do we do? Oh yeah, we got to divide Earth into north and south half. Again, that's a circle. And all the places on that line or that circle are on the equator. And I'm going to do it over here too. Might as well get that done. And I'm going to call that EQ, equator. And there's a good start. Now, what do we want to do? We want to talk about latitude first and then longitude. Latitude is, again, a little more important, and if you start to understand this, you'll see why. Latitude, I call it LT and LG, just short. Unfortunately, they're kind of similar words. We're going to see that we got azimuth and altitude, those are similar words. We've got latitude and longitude. We got waxing and waning. Those are similar words. Why? It makes it a little harder, but latitude. Latitude is how much north or south of the equator you are. And it's an angle. Now, don't overthink this too much, okay? Because you can, just go with it, okay? So remember, this is a sphere. It's a round thing, right? So think of it as from the center of the sphere. If I take it out and go from here, then I go measure the angle from the equator. So if you imagine putting this in the center of the sphere, then I would say, how far up north or how far south of the equator do you live? And we're going to talk about a bit there too. So I want to know how far north or south you are of the equator. Okay, and so I'm going to put that here and just say, well, the equator is my reference. So LT, latitude, and I'm just going to put EQ. You can use capital letters or whatever. I'm just kind of making this up, right? Is 0 degrees. because there's no angle here, and then I get more and more north angle, and here I get more and more south angle. And watch what you get. Okay. Now let's take a place here. I don't know, San Francisco. So here we go, one side of the US. We are going to talk about that. So there's SF. And think about you're in San Francisco and you want to change your latitude. Which way should you move? Well, if you want to be more north, you move north. If you want to be less north, you move south, right? So in order to change your latitude, you can move north, which would be like this, going up to Canada, where people talk. It's just because you can't not like Canada. I mean, so that's why I think South Park makes fun. Or you can move, of course, south, and that will change your latitude because you're changing how much north or south you are. Well, that kind of makes sense. Let me do this. It's on a ball, so I'm kind of curving a little bit, right? North and south. All right, cool. No biggie, right? And a repetition, don't sink in the first time, you know. Okay, and then, but what if I want to keep the same latitude? Well, then don't move north or south, and what are your options? Well, you can just stay there, or you can move east. Or west. Right? This is in the book.